Welcome back. So you'll recall that when we looked at the problem of the double negative feedback, that I invoked this idea of the fraction of transcription factors that were active, and I said that I would be giving a vignette about the so-called Mono-Wieman-Charge model, and let me write their names: Mono, Wieman, and Charge, and this is a really, super interesting story. I, over the last 10 years, have given a talk called the Other Bohr and Biology's Greatest Model, and that pertained to this particular model because I really do think that this is one of the models that has the farthest reach of anything that I've seen in the biological setting. So the point of this vignette, which is going to be a bit long actually relative to some of the others, is to try and introduce you to this particular statistical mechanical model. I need to give you some background first, and in light of that background, then we'll do some calculations, and that will provide the backdrop to what I did in the double negative, because I don't want to just quote equations without explanation. So the bottom line is that, first of all, that there are many macromolecules in cells that exhibit what I would call two-state behavior. On the left is probably the easiest of all to think about, which is that ion channels sometimes are closed and sometimes they're open. And what drives that transitioning between being open and closed is something like the voltage or the presence of tension in a membrane or the presence of some ligand, on and on. So the bottom line is that these channels can exist in two states. The next column shows you enzymes, and that's really, in some sense, the origin of the idea of allostery, and that was that in the early 60s, people started to realize that there were molecules that could inhibit or activate enzymes, and it wasn't entirely clear, is it true that every inhibitor would have to actually fit into the active site? In other words, the competitive inhibition, or was it some other mechanism? And then the activation idea was even stranger. And what I can tell you now is that we know, for example, if you look at the molecules that are engaged in the enzymatic reactions in glycolysis pathway, many of them have 3 inhibitory and 3 activating inputs, just for example. So this idea of enzymes being in 2 different states of activity, and that those 2 states of activity can be controlled by the binding of ligands is ubiquitous. Next, receptors. So here I'm thinking of chemotaxis receptors, quorum sensing receptors. We can go on, but they have different states of activity depending on whether or not there's some ligand bound. And then the problem that we're going to think about probably the most is transcription factors, and that was the context that I brought it up earlier. I just wanted to point out that the structural biologists have been very hard at work and have major achievements in understanding the structure of these allosteric molecules. Often they will have a structure in the presence of the ligand and the absence of the ligand and the active state, the inactive state, and so on. And here I show you several examples. On the left is the nicotinic acetylcholine ion channel receptor. Next is a G protein coupled receptor. The third one, the regulatory protein, is the LAC repressor. And finally is hemoglobin, which we talked about in the vignette on Figure 1 and Figure 7 theory, and closing the biological loop. Okay. So I already mentioned this idea of that the Mono-Wieman-Charge model could make an argument as being biology's greatest, not biology's greatest idea. I think I got a little carried away there. I would say biology's greatest model. I'd say biology's greatest idea is evolution. But anyway, biology's greatest model. And at the time that Monod and Jacob actually articulated this idea of allostery, Monod referred to it as the second secret of life. And I think what he must have had in mind at the time was the first secret of life was DNA. Although, again, I think we could debate that. In some sense, I would think that the first secret of life is actually evolution. At any rate, it's a little tongue-in-cheek that I made this figure, and the point of it was just to say that, we could organize our thinking. If you think about a book, a biology book, one might have hemoglobin on a very different page than the nicotinic acetylcholine receptor, which would be on a different page than some GPCR, which would be on a different page than nucleosomes, hundreds of pages apart. And the point of my little quote-unquote phylogenetic tree here is simply to say that, you could organize your thinking about biological phenomena not along lines of, that's about physiology and oxygen, but rather along lines of what the underpinning theoretical analysis is. And in some sense, which people might almost find crazy, I would say that many of these examples are the same. In the same way that a mass spring system is the same as an RLC circuit, like really the same, formally the same, even though, wow, it's so different. In one case you take a metal and you make a spring out of it, you take a mass and you look at oscillations, and in another case, you put some resistors and capacitors and inductors together, and that makes a circuit, and the way you measure that one is on an oscilloscope. But for my purposes, they're the same. And I think that kind of sameness is really one of the things that I would say, again, this is a subjective thing, but is one of the great challenges of modern biology. And I'm making a bet that in 50 years, we will see that many things that different labs that don't even think they're at all working on the same thing, we will think, oh yeah, they're just all working on the same thing. So anyway, that was just kind of by way of background. The next thing I want to say is these allosteric molecules are often, will exhibit a very generic kind of phenotypic response. And what I mean by that is that one could characterize their phenotypic response in terms of an input-output curve. This input-output curve has key observations that one can make about it. One is the so-called leakiness. Leakiness is the fact that even in the absence of effector, you get some output. In other words, if this thing were not leaky, then the input-output curve would come all the way down here to 0. And I'm just saying that if you look at the real world of molecules, most of them don't go down to 0. So they're leaky. They have a little output even in the absence of input. This axis is the input of the ligand. And the next thing I want to comment on is what I will call the EC50. What is the concentration of effector at which they have their midpoint of activity? Next is the slope. How steep is this curve? The reason that's important, it tells you to what extent it's got switch-like response. And then the dynamic range is telling you about the difference between the leakiness and the saturation. How much oomph is there to be had as a result of the binding of effector. So this is a challenge to us as theory, and I also think it's really exciting from the standpoint of evolution because in some sense, the fitness, I would say, one could imagine a fitness which is dependent upon these key parameters. And so in some sense, your fitness model, instead of referring to the positions of atoms or which residue is present in a given protein, would instead focus on the saturation, the leakiness, the EC50, the effective field coefficient, and so on. Okay, so this is just to give you a sense that this is from a paper of Noah Goldman and Leah Giantoro, where in PNAS, and what I like about it is that they give us several cool, really interesting indications here. One is, these are 6 different examples of input-output curves, just like I was showing you a moment ago. And you can see, obviously, their EC50s are different. It also shows you that there's ways to tune these things. Like I'm going to focus on this one. This is a very deep thing about biology. If I build a generic receptor molecule, it has a KD, and the binding curve will look like this. And that's it. It's got a binding curve. The thing about these biological examples is that they can change their behavior depending upon whether or not there is methylation, for example, or the pH changes or whatever. You can see that in the case of hemoglobin. So it's a very beautiful thing, and maybe I'll just put the word note. Huge challenge here. Biologically important adaptation. These things change in response to some sort of environmental tuning. Okay. So, just playfully, if you go to Wikipedia and you search Janus, you'll see that this is a Roman god, the god of entrances and exits. And, it's just kind of funny to imagine allosteric molecules, Janus molecules. I also wanted to say, that this very notion of feedback is, really an important idea. And it's an important idea in all sorts of different settings. In the 1800s, as shown here, there were mechanical governors. And these mechanical governors spun around, and if they got spinning too fast, then that would basically repress the system by tuning how much steam there would be, for example. And, we're used to our toilets even as having active and repressed states. And so, just generally I want to point out the importance of feedback. Okay. Still just giving an introduction to allostery and the broad reach of the allosteric phenomenon. So here I'm giving you three different examples: a metabolic example shown here, a cell motility example shown here, gene regulation example shown here, and then a motility example shown at the bottom. And the idea in all three cases is just meant to show you that the pathway can either be active or inactive depending upon the presence or absence of the ligand, as an exterior signal. So just wanted to make that clear, that that's the kind of thing where this allostery idea comes into its own. Okay. So what we're going to do now is we're going to go down the path of our statistical mechanical thinking about these kinds of problems, and you'll recall that our point was that we want to write down the states, we want to write down their energies, then we want to write down their multiplicities, and then we want to write down their statistical weights. And here I just wanted to kind of introduce the action in these allosteric molecules so that you can get a sense of what's going on. So over here, I'm showing you, let's call this the inactive state, the active state. And what you can see is that there's either the active but unbound or the active but bound configuration. And over on the right-hand side, I have the inactive and unbound and the inactive and bound configurations. Note something different than our previous treatment of ligand-receptor interactions, and that is that there's an EA for these two guys, and there's an EI for these two. What that means is that the equilibrium configuration, it will be dependent upon the relative values of EA and EI, or epsilon A and epsilon I. If epsilon I is lower than epsilon A, then at equilibrium and in the absence of ligand, then the inactive guy will be favored. On the other hand, now let's imagine that epsilon binding A, so that's this quantity, this tells me the binding energy of a ligand. If that's more negative than epsilon binding I, then the consequence of that is that the binding of ligand will tune the equilibrium and will now favor the active state. And that's the essence of this whole model. So here what I'm showing you is I'm just asking you to kind of go back to what we did earlier in terms of states and weights. And so, if this is the energy of this state, epsilon I, then the energy is e to the minus beta epsilon I, which is what I have written. If this is the active and unbound state, then it has a statistical weight as shown here. Then, imitating what we did earlier, where I used the C over KD as my way of signifying the weight in the presence of ligand, you can see that I can write these weights. And so if I wanted to write, for example, P active as a function of C, how would I do that? I would say that it's equal to e to the minus beta epsilon active, and then 1 plus C over KD active. And then that's over the same quantity. And then plus except now the A's become I's. So this is epsilon I, this is KDI. And so that's our fundamental equation for an allosteric molecule that has one binding site. This is it. And it's a really profound equation. And one of the things I want you to notice about it is that if KDA and KDI were equal, if that were true, the things in parentheses would cancel out, and this and P active would not depend on the concentration of ligand. So the super subtle idea that Monod, Wyman, Changé had was that the binding constants are different in the active state and in the inactive state. That's very, very important. That's subtle, and it's not obvious. I'm not sure I would have thought of such a thing. And so, this is what the activity curve looks like. You see that here. And then also for fun, what I did is I plot the probability of the four states. And there's four states of occupancy, right? There's inactive, or sorry, yeah, inactive and unbound. There's active and unbound. There's inactive and bound, and there's active and bound. So those are the four states. And what we're doing here is we're plotting the probabilities of all four of those as a function of ligand concentration, which is on the x-axis. That gives you an impression of what's going on with this thing. I just wanted to also say that that we can think about this from a free energy point of view or an energy point of view. Remember that the Boltzmann distribution tells me the probability of a state goes like e to the minus the energy of that state. And what I'm plotting here is I'm just trying to show you that the energies of the red and the blue states, this guy is the one that is favored when there is no ligand. And the reason it's favored is because we're over here, and red is below blue, which is below yellow, which is below green. So red is the winner over at low concentrations, right here. On the other hand, at very high concentrations, the yellow guy now is the winner. It has the lowest energy. And the reason is because the binding energy of that guy is so favorable that it ends up carrying the day. And in between, there's some intermediate region where all four states have some weight. But my point is that at low concentration, this state wins. At high concentration, this state wins. And you can see that by looking at the concentration dependence of the four state energies. Two of them, these two, are independent of concentration because there's no ligand bound to them. But these two states definitely depend on that. All right, so the point of this little series of graphs is I'm just flashing it for a moment to point out that there's many phenotypic properties of these molecules, and there's formulae for them. We can work them out on the basis of this Monod-Weinmann-Schanja model, and I probably will ask you to work out some of them in the context of an upcoming homework. But this is mainly for the purposes of knowing about as opposed to knowing. I'm not trying to overwhelm you. I'm trying to acquaint you. It's like saying, yeah, if you've never been to California before, then the sort of thing I might do is I might say, well, there's a little bit of a cultural gap between Northern and Southern California, and there's the coastal region and there's the Central Valley. I may not have taken you to all these places, but at least I would kind of give you the lie of the land, and that's what I'm trying to do with this thing. I'm just trying to give you the lie of the land for Monod-Weinmann-Schanja models, and to point out that we can compute all sorts of interesting phenotypic properties, and they depend upon the parameters that I've introduced: C, Ka, Ki, delta epsilon, the energy difference between the active and inactive states. So what I want to do is I just want to finish up on a quick note of how we would use this model in the context of thinking about transcription factors. So I wanted to point out, this is just to show you that there are all sorts of examples of inducible transcription factors. This is for E. coli, where in the presence of some allosteric effector, we tune the activity either by taking a transcription factor which is inactive and making it active, or alternatively taking one which is active and making it inactive by virtue of the binding of an effector, which is what's shown over here. You can see increasing inducer leads to larger gene expression because, as you see here, in the presence of the effector, the repressor falls off the DNA. So this is the kind of thing that we want to calculate. So once again, we're faced with our usual prescription, which is we need to compute the states and weights. And the way that we do that is we acknowledge the states. So here are the four active states. The reason there's four is there's two binding pockets, which I show you here. And the transcription factor can either be empty, it can be bound on the left by a ligand, bound on the right by a ligand, or doubly bound. And those have these four respective statistical weights. And then it can be in the inactive state, as I show on the right-hand side, similarly with four states of occupancy. And the statistical weights are given here. And this means that if I wanted to write P active as a function of concentration, then it's going to be given by this quantity. So 1 plus C over Ka quantity squared over 1 plus C over Ka squared plus e to the minus beta epsilon 1 plus C over Ki squared. And this is precisely the formula that I used earlier in the context of the double negative switch, where I told you later on I would justify it. And that's what I'm doing now. So the justification is that there's 8 states of occupancy and conformation associated with an allosteric transcription factor with 2 binding sites. There's 4 active states. There's 4 inactive states. We know how to write down their various statistical weights. And then by the usual rules of probability, which tells me if I want to find the probability of a thing, in the numerator I take the statistical weight of all of the states, or of all the states that are consonant with the thing that I want, and the denominator is the sum over all the states. That's the concept, and that's what I've done here. So the numerator is the sum over all the states of activity. The denominator is the sum over all the states. Now, if you're paying attention, you might say, hey, before you had epsilon I and epsilon A, I've basically amalgamated them in one parameter, epsilon, because really all that matters is the difference between epsilon I and epsilon A. This theory is very predictive in a super interesting way. And what I'm showing you here is the use that can be made of this theory to look at gene expression in the presence of the repressor. And these 3 curves correspond to 3 different graphs correspond to 3 different DNA binding energies. So maybe I should write that. Different graphs correspond to different repressor binding energies. And then within a given curve, there's different numbers of repressors per cell. So here, on the left, this is the case of strong binding to DNA. And what you can see is that if you have lots of repressors around, here or here, and strong binding, then this thing never gets very much gene expression. Because even with lots of IPTG, it's still binding. Some of them are still binding to DNA. So it's repressed. Over here, this is weak binding of the repressor to DNA. And you can see that means there's lots of leakiness. That means that even in the absence of inducer, there's not that strong a binding of the repressor to DNA. And so you don't get enough repression. This one particular graph is the one we use to fit the parameters Ka and Ki that I mentioned a little bit ago. At that point, the theory is predictive. There's nothing left for us to do in terms of predictions. I just wanted to point out, I'm not gonna belabor it, but we had a paper in which we performed these measurements, and the outcome is shown here. And I'll leave it to you to decide whether you think it's worth our while or your while or somebody's while to spend a couple of grad student years to explore some of the discrepancies. I'm circling some of the discrepancies between theory and experiment. These are all parameter-free predictions. And I think, that makes them figure 1 theory predictions, to use the previous language. So, in that sense, it's very exciting and very interesting. But at the same time, the slope here seems to be more shallow than we predicted. And, I think that's interesting. I think, at this point, that's probably a good enough introduction as a first pass on allosteria and the Monod-Weyman-Changé model. So, just as a kind of reminder, what I told you here was that there's a simplified model of two state macromolecules in the cell, and so that's the allosteric model. There's a very generic sort of input-output response of such molecules, and the intrinsic parameters of these responses are things that we can calculate from the theory, and I will actually suggest that in an upcoming homework. So with that, I call it quits.